Good day, I'm Norman Wildberger. In our last video we introduced the idea of arrays as lists of lists, and I mentioned that there's another way that we're going to have of thinking about objects which are like arrays, namely matrices. So in today's video I want to have an overview of the standard approach to matrices, which of course play a very big role in linear algebra, objects like this. And then at the end we're going to move towards a very novel approach to the definition and the understanding of what's going on with matrices like this, and in fact the overall setup of linear algebra. So we are going to be moving towards a position where when you look at something like this, you're going to think about it in quite a new way. Okay, it's going to be a sort of a seismic shift in your understanding and orientation towards these very fundamental objects in mathematics. So very exciting stuff happening today. So let me overview the traditional point of view towards matrices, which are core objects of linear algebra. So this is really very much part of the setting up of basic linear algebra. If you are interested in learning a little bit more about linear algebra, I recommend my YouTube series, Wild Lin Alg, which gives an elementary approach to linear algebra from a geometrical point of view. So traditionally in a linear algebra course, one starts with objects like this, defined in a very visual way. We say that an array of numbers, a table of numbers of this particular form is a matrix, and we talk about its dimensions being 2 by 3. It's a 2 by 3 matrix because it has 2 rows and 3 columns. Here, for example, is a 2 by 2 matrix. You see that the entries could also be rational numbers, negative numbers. Here's another 2 by 2 matrix which plays an important role. The identity matrix, which is 1, 0, 0, 1. That's a 2 by 2 identity matrix. Okay, so there's a number of basic things that we can do with matrices even at this introductory level. If we have matrices of the same size, then they can be added, subtracted, and multiplied by scalars or numbers. So here are two matrices of the same size. They're both 2 by 3 matrices. To add them, we just add them component-wise. So the top left entry here and the top left entry there add to give the top left entry there. This 1 by 2 entry and this 1 by 2 entry here combine to give the 1 by 2 entry there. All right, so we just do everything component-wise. It's very simple. Subtraction is exactly the same. If we take this 2 by 2 matrix and subtract this 2 by 2 matrix, you get 5 minus 1 is 4, 8 minus 9 is minus 1, minus 4 minus 2 is minus 6, and 7 minus 5 is 2. And the other thing that we can do is multiply a matrix with a scalar, or a number. So 6 times this matrix is what you get when you just multiply each of the elements by 6. If we only had addition, subtraction, and scalar multiplication, then matrix arithmetic wouldn't be that interesting and that useful. What makes it really important is that there's a matrix multiplication as well. So here's how we multiply matrices. It's not what you might think. It's not pointwise multiplication. So here's a 2 by 2 matrix and here's another 2 by 2 matrix. We can form the product. That's, as it turns out, another 2 by 2 matrix. But it's not the case that this 62 here is the product of 2 times 1. Rather, to get this 62 here, what we do is we multiply the first row in the left-hand matrix with the first column of the second-hand matrix. And we do that in a very particular way. We take the 2 here and we multiply it by the 1 here, 2 times 1, and then we add the product of 5 times 12. So we have two products, the product here and the product here, and we add those two products to get a total of 62. Now when we move over to this entry here, we are still sort of multiplying rows by columns, but now it's this first row here multiplied by this second column. So it's 2 times 7 plus 5 times 4 for a total of 34. And then down here, minus 30, we take this second row times the first column. So 6 times 1 plus minus 3 times 12 is minus 30. And finally, this 30 here is this second row times the second column. 6 times 7 plus minus 3 times 4, a total of 30. So in each case, we're multiplying a row by a column. And there's 2 rows and there's 2 columns in this case. So there's 2 times 2 equals 4 possibilities, and there they are there in that matrix there. So this operation is often viewed as an extension of just a sort of more elementary operation of just multiplying a single row vector by a single column vector. So if we have, say, a slightly larger vector, a vector with 3 components there and 3 components there, we can also multiply these two. The important thing is that they have the same size. So the way we multiply these two vectors, this row vector by this column vector, is again to take 1 times 2 plus 3 times minus 5 plus 7 times 4. So we're forming a sum of products. In this case, that happens to be 2 minus 15 plus 28, which is 15. In that case, it's just a single number. And in the matrix world, we like the output of products to be matrices, so that would be a 1 by 1 matrix, which is just that number with the brackets around it. So matrix multiplication in general is really repeated operations involving the same basic operation of multiplying a row by a column. And we basically go through all the possible rows of the left-hand matrix, all the possible columns of the right-hand matrix, and we write down each of those various possible products in the product matrix. Now the n by n matrices, so if we take matrices which are square, they have the same number of rows and columns of a fixed size, then they form an algebra. That means we have the operations of addition and multiplication and subtraction and division too, at least partially. And there's relatively pleasant laws of arithmetic that parallel the usual laws of arithmetic for normal numbers. So for example, the addition is commutative. A plus B equals B plus A. It's also associative. A plus B plus C equals A plus B plus C. However, the multiplication, which is a little bit more subtle, does not have the commutative property. This is a very important point. So AB is not in general equal to BA. Sometimes it can be, but typically it's not. Nevertheless, the associative law for multiplication does hold. And this is a quite interesting and almost remarkable fact. It's not entirely obvious at all that that rather complicated multiplication that we got by multiplying rows and columns and repeating, that it has this property that if you take AB and then multiply that by C, it's the same as multiplying A by BC. There are also distributive laws in either case, and there are some laws having to do with scalar multiplication, what happens when you multiply a matrix by a scalar. It's also useful to mention this identity matrix in general. So if you have an n by n situation, here's the corresponding n by n identity matrix. It has ones down this diagonal. It's called the diagonal, and everything else is a 0. So this identity matrix has the property that when you multiply it by any matrix A of the same size, in either order, you get the other matrix. You might like to check that that's the case. It's an interesting check of the matrix multiplication. Now what about division? So there is a partial kind of notion of division around, and it's a little bit more subtle than one might think. So it turns out that some matrices are invertible and some aren't. So invertible means that you can find another matrix, say B, so that A times B is the same as B times A equals the identity matrix. So we're finding a sort of an inverse. B would be called the inverse of A. And it has to be a two-sided inverse so that it has the property that you can multiply it by A on either side and get this identity matrix. This identity matrix is playing the role of 1. So this is sort of the matrix equivalent of taking the reciprocal of a number. So it turns out that to tell whether a given matrix is invertible or not is rather a subtle issue and depends on the determinant. So it happens just when the determinant of A is not 0. What's the determinant of a matrix? Well, for a 2 by 2 matrix, it's relatively easy to say. The 2 by 2 matrix A, B, C, D has determinant AD minus BC. we've seen that expression before. For higher, bigger matrices, the corresponding definition of determinant is more subtle. So the theory of matrices then sort of overlaps considerably with this theory of determinants, which surprisingly really sort of came before the theory of matrices themselves were sort of officially brought into being. So determinants were much studied in the 18th and 19th centuries. Okay, so there's pleasant kind of structure in the arithmetic of n by n matrices where you fix an n. So I'm giving a rather brief overview here of stuff that takes weeks to lay out in a linear algebra course. But a natural question is, what are these matrices good for? Why do we need them? Well, they arise in linear algebra as concrete examples of what are called linear transformations. And I can illustrate that perhaps in an example here. So here's a 3 by 3 matrix, let's call it A. And here is a 3 by 1 matrix, which is also called a column vector. We call that V. Now we can multiply this matrix A by this column vector in the same kind of way as we were talking about before. We're going to multiply the rows of A by this single column. So the first row times the column would be 3 times 1 plus 1 times 4 plus 2 times 4. So 3 plus 4 plus 8 is 15. Then the next entry would be this row times the same column. So that's 2 plus 0 plus 10, for a total of 12. And then the last entry would be the third row here times this column, minus 1 plus 24 minus 4, for a total of 19. So what we get is another column vector of the same size in this case. Call it W. So the equation can be written as A times V equals W. And we can interpret this as something happening to V to change it to W. So in functional notation, if we allow ourselves to use this temporarily, so W is equal to T of V, telling us that we start with V, sort of the input, we apply this transformation, in this case multiplying by this matrix A, and then the output is this other vector W. So this transformation, going from this vector to this vector, has two important properties that define what's called linearity. So the properties are that T of V1 plus V2 is T of V1 plus T of V2. And secondly, that T of lambda V equals lambda T of V. These two properties define what we mean by a linear transformation. And then it turns out that any linear transformation from a three-dimensional space to itself is necessarily of the form this, for some 3 by 3 matrix. So the linear transformations and the matrices become basically the same things. This linear transformation and this matrix are almost the same thing. And that's really a motivating reason why matrices are studied, because they represent linear transformations for us. Linear transformations could be things like rotations of three-dimensional space, or maybe reflections, or maybe some kind of shears or dilations. So it's a very pleasant, powerful algebraic arithmetic that actually encodes these geometrical movements. It's a very nice idea, very powerful idea. So again, if you'd like some more detail about linear algebra, I suggest having a look at my Wild-Linalge series. So what we've just been talking about, this idea of having a matrix and then getting a linear transformation, we had an example that was in the n by n case. Actually, it was 3 by 3. It turns out that that correspondence extends in an important way. It generalizes to linear transformations between different dimensional spaces. And that ends up corresponding to matrices which are not necessarily square matrices. Say m by n matrices with m rows and n columns. Such a matrix turns out to correspond to a transformation from n-dimensional space, Vn, to m-dimensional space, Vm. So let me illustrate that. Here's a 2 by 3 matrix. And we can multiply that 2 by 3 matrix by a 3 by 1 matrix, or a column vector, on the right. We need to have 3 here because there's 3 here, and the way we multiply the row and the column, we need the same number of entries here as are here. So if we do this multiplication, we get 12 minus 2 minus 18 for a total of minus 8, and 21 minus 1 plus 30 for a total of 50. But notice that in this case there are only 2 outputs because there's only 2 rows. So we've started with a 3-dimensional vector and we've ended up with a 2-dimensional vector. And that's no surprise, that's because we were multiplying by this 2 by 3 matrix. So the 2 by 3 matrix takes a 3 vector to a 2 vector. Okay, so now we can appreciate why matrix multiplication is important now. Because now that we have this association of matrices with linear transformations, there's a very natural thing that we can do with linear transformations, and that is to compose them. So if we have one linear transformation, say from V2 to V3, and another linear transformation from V3 to, say, V2, then we can compose them. It means we can do first this one and this one. Then the composition will be, as it turns out, another linear transformation. A third linear transformation that just takes this vector and gives you a vector here. And it turns out that this composition of linear transformations corresponds exactly on the matrix side to the matrix multiplication that we introduced earlier. That's why matrix multiplication is important and useful. So for example, in this situation here, suppose that A was this matrix 4, 2, minus 3, 7, 1, 5, and B was some other matrix, in this case a 3 by 2 matrix, 1, 2, 0, 2, minus 1, minus 3. Then I'll let you check that the product of these two matrices is C. And this product of matrices corresponds on the linear transformation side to this diagram here. Multiplying by B would take a 2 vector to a 3 vector. And then multiplying by A, just as up here, would take a 3 vector to a 2 vector. So multiplying by B first and then by A, the total effect is to take a 2 vector to a 2 vector. And that turns out to be a linear transformation whose matrix is exactly this 2 by 2 matrix C, obtained by multiplying A and B. So composition of linear transformations corresponds to multiplication of matrices. And that's why matrix multiplication is important. And it's important also that this matrix multiplication is flexible enough to deal with matrices which are not necessarily the same size. The crucial thing is that the number of columns, in other words, sort of the width here, equals the number of rows here, so the height here. Because we need to be able to multiply these two matrices. We're taking this times this, plus this times this, plus this times this. In order for that to work, there's got to be the same number here as there are here. So you can't multiply any two matrices. The dimensions sort of have to match up. The inner dimensions have to match up. So matrix algebra is a little bit richer than we might at first think, because of this fact that we can multiply matrices of different sizes. And in terms of the sizes, here's how it works. So if A is a K by L matrix, and B is an L by M matrix, then A times B equals C is well defined. It's because there's an L here and there's an L here. These two numbers are the same. That allows you to multiply the two matrices. L will be the number of columns in the first matrix, the number of rows in the second matrix, and that allows you to make those products of row vectors by column vectors. And the result then is the matrix of size k times n, which is the other two numbers which are involved, the k and the m. So this is now then in addition to the arithmetic of the individual matrix algebras, the 1 by 1 matrices, the 2 by 2 matrices, the 3 by 3 matrices, and so on. Each of these is a well-defined little domain of arithmetic. So just inside the 3 by 3 matrices you can do all these operations. Just inside the 2 by 2 matrices you can do all these operations, and so on. So, but in addition, you can also multiply these sort of non-square type matrices, which otherwise don't really fit into this situation here. So it's a rather rich arithmetical structure, all of these matrices floating around. So we've had an overview of matrix theory as it's usually presented in a linear algebra course, and very interesting and important topic. But what we would like to do is to move the subject in a little bit of a different direction by bringing to the fore some combinatorial, essentially data theoretical structures which are sitting underneath the matrix theory, which are perhaps not entirely visible these days. So we want to make them visible and give them the stature that they deserve. This will clarify lots of things, okay, and it will open our eyes to a larger vista for matrix theory. So, a new look at matrices. The first new definition is that of a pixel. Usually a pixel is something that we associate with a little point in a digital diagram, and its meaning here is in that direction as well, as we'll see. But officially for us, a pixel is going to be a two-list from natural numbers. A two-list from nat. That means it's a list with two entries, each of which is a natural number. So here is A is a pixel. Here is B, it's also a pixel. These are lists, so they're allowed to have repeated entries. Now, we have seen these kinds of things before, of course, because these look just like points. Points from affine space or from Euclidean geometry. And they are very much like that. Those are also two lists. But here we're restricting the elements to be in natural numbers. And we're using slightly different notation, and certainly different terminology. Remember that 0 is not officially a natural number. So the smallest pixel is this one here, 1, 1. A few other definitions. So a pixel of the particular kind NN, where the two entries are equal, will be called a diagonal pixel. And for a pixel A equals MN, one natural thing that we can do with this thing is just to swap the two entries, and we're going to give that a name. So we'll call that the transpose. And we'll denote it with an A with the superscript T, capital T. So that refers to the transpose of A, and there it is there, it's NM. So we've defined some new objects, and let's give these new objects a type name. Okay, so the type now will be pix. And you can think of pix as being a natural two-dimensional generalization of natural numbers. Natural numbers just go 1, 2, 3, 4, 5, so on, in sort of one direction. Now we're allowed two directions. We have a first coordinate, a second coordinate. They're both natural numbers. This is going to be a pretty interesting type of object for us. And now let's talk about visualization. We're human beings, we like to draw pictures. So how are we going to visualize pixels? Well, let me remind you of natural numbers. In natural numbers, we can visualize them just by having a list, sort of a discrete number line. 1, 2, 3, 4, 5, and so on. We can extend. We want to consider a two-dimensional version of this, because pixels are really just a two-dimensional version of natural numbers. And we're going to do that by introducing this particular notation. We're going to call this the screen. Okay? The screen is going to be a particular way of organizing pixels. Starting up here in the top left. So increasing the second coordinates as we go to the right along a row, and increasing the first coordinates as we go down along a column. So here is 1, 1, then 1, 2, 1, 3, 1, 4, and so on. So we could extend. And then the next row, 2, 1, 2, 2, 2, 3, 2, 4, and so on. And then 3, 1, 3, 2, 3, 3, 3, 4, and so on. And then we could keep going. Next one would be 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and so on. So this is a visual guide, a visual aid that helps us picture this new type that we've just defined called pix. And we refer to this visualization as the screen. And this screen gives us that pix is really a two-dimensional version of nat. Natural numbers, pix, they're naturally related. That's a one-dimensional, discrete kind of framework. This is a two-dimensional, discrete kind of framework. But it's important that we adopt the convention that we're starting up in the top left and that we're going to number things or label things in this order, just as we've shown here. So now we come to the main definition, which is going to underpin our new approach to the algebra of matrices and that section of linear algebra. We're going to introduce this concept called a maxil. Okay? So maxil is supposed to rhyme with pixel, and there's a close connection. So a maxil is by definition a multi-set of pixels. So we're using our data structure point of view of the various LOMs. We're choosing multi-set. So for example, here is a multi-set consisting of pixels. The pixel 1, 1, 1, 3, 2, 2, 1, 3, 2, 4, and 2, 4. Notice that there's no commas, telling us that rearrangement is allowed. And also repetitions are allowed because of the brackets on the outside. So there are 2 1, 3s. We could also see 2 4s. Okay, so these are going to be fundamental objects for us. And we want to visualize this thing. Okay? And we're going to visualize this maxil by recording its multiplicities on the screen. We're going to do very similar kind of thing to what we did when we were talking about multi-sets of natural numbers and corresponding lists, where we could count the number of 1s, count the number of 2s, count the number of 3s, and so on in a multi-set, and then associate to that the list of multiplicities. We're doing the same thing here, except that now we have a kind of two-dimensional representation of the multiplicities because the objects themselves form this two-dimensional grid, actually what we're calling a screen. So here is our screen, which is just a way of organizing our various pixels. And so now we can have a look at what are the various multiplicities of these pixels in this multiset M. 1, 1 occurs once. So we put a 1 in that position. 1, 2 occurs 0 times. 1, 3 occurs twice. And 1, 4 occurs not at all. Then 2, 1 occurs not at all. 2, 2 occurs once. 2, 3 doesn't occur. And 2, 4 occurs twice. At this point we can stop because we've recorded all of the objects in this maxil. So while in principle we could go on and extend, we would only be adding zeros by doing so. So this already encaptures the multiplicities in our maxil. And we'll write this in a somewhat familiar way. And we recognize a matrix. So this suggests to us that this matrix can be thought of now as actually representing multiplicities of pixels in a maxil. So matrices are appearing here in quite a different way. A matrix is in this sense, just a picture of a maxil, and we're going to see that these maxils allow us to reformulate a lot of interesting things about linear algebra, and especially matrix algebra. So in our next video, we're going to look more at maxils. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.